This is a fully programmable Turing-complete 8-bit breadboard computer, capable of being programmed with 16 different consecutive instructions. The following video will consist of a quick introduction of how the computer works, followed by a demonstration of this computer in action. I would like to give credit to Ben Eater for his 41-part series, where a lot of the ideas and inspiration came from. For the most part, this is still my own design. Moving on, this computer consists of 10 different components: the clock, the RAM, the control register, the output, the B register, the A register, the ALU, the counter, the control logic, and the bus. I'm going to give a quick description of how the clock and RAM components work within this computer. The clock. In short, this component controls the speed at which everything works at. Basically, whenever the clock ticks, there's a transfer of data from one component to another component through the bus. When this switch is to the left, the clock ticks on its own at a variable rate, and when it is to the right, it is in manual mode where it ticks on the push of a button. The RAM component can store 16 different 8-bit values that can be accessed from this 4-bit address. The value at that address is seen here, where it can later be put onto the bus. The RAM has two modes, the red mode and the green mode. When the switch is to the right at the red mode, it allows for the RAM to be manually programmed. To do this, this dip switch is used to set the address, and this one is used to change the value. On the click of the button, the value at the RAM address is changed to the value set by this dip switch. When the mode is in the green mode to the left, the function is the same, but it takes input from the bus instead of from the dip switches. To demonstrate the capabilities of this computer, I am programming it to do the Fibonacci sequence. The Fibonacci sequence is a loop where x and y are added together, and then the product is set to y and y to x. In this case, the program outputs y before every addition. In this program, the RAM position 15 is used as the variable to store the y value between loops. Here, the computer jumps to instruction 0 by setting the counter to 0. At instruction 0, the program sets the A register to have the value of 1. Instruction 1 writes the A register's value to RAM address 15. Instruction 2 loads the A register with the value 0. Instruction 13 outputs the A register. Instruction 4 loads the value at RAM address 15 into register B. Instruction 5 jumps to instruction 0 if the product of register A and B overflows, which it doesn't. Instruction 6 adds register A and B together and then puts the product into register A. Instruction 7 writes the A register's value to RAM address 15. This stores Z into RAM to later become Y when it is read from in instruction 4. Instruction 8 outputs register A. Instruction 9 moves a value in register B into register A. This is the Y to X process. Instruction 10 loops back to instruction 4, so the process can start over and can continue going through the Fibonacci sequence over and over.